All right, hi everyone. How's it going? Last time we were talking about the substitution rule, aka U substitution. We did many examples with the indefinite integral where we use U substitution, and we left off with an example where we did the definite integral, meaning we had an A and a B, and we did this process. It's a little subtle what you're supposed to do with the limits of integration. So let me do one more example just to really solidify this. So let's say we want to find the following. So we want to find this integral. Okay, for a second, let's just ignore the limits of integration and just think how we're going to solve this with U substitution. Here, you literally don't have many options for U. It's almost immediate what it should be, the only thing that it can be. So we're going to let U be the 3 minus 5x. And so remember, that means when we take the derivative, we get du is the derivative of this, which this is 0, and then the derivative of negative 5x is just negative 5. So this is negative 5 dx. And then when we divide by negative 5, we have du over negative 5 is dx, okay? So the dx will get replaced with that. This whole expression will get replaced with u. Now, because 1 and 2 correspond to when we were using x, we need to figure out what 1 and 2 are. They're going to be different numbers in general when we use u. So notice that u is actually a function of x, right? U is a function of x. That's how we write it mathematically. And remember what that means is if I give you a value of x, you get a corresponding value of u. U depends on the choice of x. So it's a function of x. So when x is 1, what is u? Well, just stick 1 in here, so we get 3 minus 5, which is negative 2. And then when u is 2, what do we get? We get 3 minus 10, which is negative 7. Okay? So now these will be the new limits of integration. 1 will get replaced with negative 2, and 2 will get replaced with negative 7. So this integral now becomes the integral with the new limits of integration from negative 2 to negative 7 and then 1 divided by u squared, right? This is u, so it becomes u squared, and then dx gets replaced with this, so it becomes du all over negative 5. Okay? And then we're going to do some manipulation of this. Remember that du over negative 5 is the same thing. This is just the same thing as 1 over negative 5 times du, correct? And so we're just going to pull this negative 1/5 out in front of the integral. So this is negative 1/5. And then we're going from negative 2 to negative 7. And then you can rewrite 1 over u squared as u to the negative 2 du. And now we're in business. Okay, so the same concepts that we've been using. We use the power rule. So this is negative 1/5 times 1 over negative 2 plus 1, u to the negative 2 plus 1, all evaluated from negative 2 to negative 7. Okay? And then we can do a little bit of manipulation here. So negative 2 plus 1 is just negative 1, right? So 1 over negative 1 is negative 1. So we have this whole thing is negative 1 times negative 1/5 just makes this a positive 1/5. So when the dust clears, this really is just positive 1/5 u to the negative 1, basically. Which, remember, u to the negative 1 is really just 1 over u. So this, okay, and evaluated from -2 to -7. And then this is the same thing as 1/5. So 1/5 times 1 over u, what is that? You just multiply these guys to get 1 over 5u. Okay, so we have 1 over 5u. That's evaluated from -2 to -7. And then what is this? Well, this is 1 over 5 times -7. Right? This is like b, so you stick this into the function and you subtract it from what you get when you stick -2 into the function. Okay, so then this gives overall -1 over 35, correct, minus, and then the minus was already there, but from here we pick up another minus, so minus a -1 over 10. Okay, so this really ends up being, because two negatives make positive, so we have 1 over 10 minus 1 over 35. Okay. And then now, you can get a common denominator and do, the arithmetic that you need at this point. So what's a common factor between these? Well, if you multiply this top and bottom by 7, and then the top and bottom of this by 2, right? Because their common factor, like for example, is 70. So this becomes 7 over 70 minus 2 over 70, which is 5 over 70, which is just going to give you 1 over 14, I believe. Yes, so it just gives you 1 over 14. Final answer. Okay, so the calculus stops at this point after we do this, and then the rest is arithmetic. So I'm sure you know how to handle this, but it's good to just go over it just to see how careful you have to be with these minus signs and things like that sometimes. Now, remember at the end of the last lecture, I said you can find this an alternate way. So you don't have to use the old limits of integration if you don't, the new ones, sorry. You can use the old ones if you substitute back. So this was the antiderivative, right? 1 over 5u. This was antiderivative, or integral basically. So if we substitute back, we really have 1 over 5 times what was u? U was 3 minus 5x. And then now, instead of evaluating this at the new limits of integration, you could have just used the original ones. The original limits of integration, which were from 1 to 2. Okay, and let's see if we get the same answer. So this is going to be 1. Well, you stick 2 into here. 3 minus 5 times 2 minus 1 over when you stick 1 in here. Okay. So that's what this is equal to. And let me rewrite this here and change the colors just for clarity. So let me make this blue. 1 to 2. And then, so this is 1 over 5 times 3 minus 5 times 2 minus 1 over 5 times 3 minus 5 times 1. Okay. So right, you just stick these two numbers into this function and take their difference. Capital F of B minus capital F of A, remember, from the FTC. So this is 1. So this equals, 1 over, so this is 10, right? 5 times 2 is 10. And then 3 minus 10 is negative 7. So we get 5 times negative 7 minus 1 over 5 times negative 2. And this was the exact expression that we had when we did the substitution. When we just stuck with U, this is the exact terms that we had. Because this was like B and this was A. So, of course, we're going to get the same answer. So, either way, you'll get the same answer. And it's up to you and your choice how you want to do this. If you want to substitute back or if you want to use the new limits of integration. It's up to you. Okay, so we're almost done with this section now. And now we're going to have to establish an extremely important property about integrals, which, if you look at a picture, it makes perfect sense. And so it may seem at first like not that amazing of a result, but it's used all over in a field of math called Fourier series and Fourier analysis and things like that, where that's like a huge field of math because it applies to a lot of problems in engineering and physics. It can model like signals, acoustic waves, sound waves, a lot of different types of oscillatory motion, like heat even. It can model heat. So it's very amazing how, it's a huge field and I'm sure you've heard of it. But this property here gets used very heavily in the study of Fourier analysis and series. So here it is. So property 1 is this. So an even function. So remember, what was an even function? So we have an even function. So an even function was a function where the output of numbers who are negatives of each other is the same, i.e. this is what it means to be even. It means that f of negative x equals f of positive x. So the output at negative x and x is the same. And because of this is the key property of your graph. For example, this function, f of x equals x squared, is an even function. Because, for example, f of 2 is equal to 4, and f of negative 2 is also equal to 4. So this is like x, negative x. See, numbers who are negatives of each other have the same output. The key property is an even function is symmetric about the y-axis, meaning that if I flip it about the y-axis, it should be unchanged. So if you get this curve, right, and you flip it about the y-axis, it looks exactly the same. So it's symmetric about the y-axis. That's the key thing about that we're going to be using here about it. This is its actual definition so that you can determine whether a function is even or not if you have the formula. But from the graph, this is how you would determine it, is if it's symmetric about the origin or not. So if you have the explicit expression for the function like this, you can tell me if it's even or not using this property. And if you have the graph, then you could tell me by the symmetry property. Is it symmetric about the y-axis? If I flip it about the y-axis, does it look any different? And that's the one we're going to use here. So symmetric about y-axis. So that's what it means to be even. So then this is going to be true. this is the key property here that we need to look at. And again, a lot of math is just kind of understanding the symbols. This looks super intimidating at first, but if you think about what it's telling you, it's very crystal clear what's going on. So another example of an even function is cosine. So let's look at cosine x from negative pi to pi. So these two numbers have to be the same. That's negative a and a. So they have to be the same. One is just negative of the other. And so since cosine is an even function, we know it's symmetric about the y-axis, right? And like if we plot it, it starts out at 1, and then at pi over 2 it hits 0, and then at negative pi it's down at negative 1, sorry, at pi. So, and then the same thing happens since it's symmetric about the y-axis. It's an even function, it has to have the same exact behavior. Okay? So, this thing here, in our case, is the corresponding area right here. Maybe a different color. Is the net area here that we get. So the sum of these negative areas along with the positive, so the net area that we get. What this is saying is that to find this overall area, you can just look at one half of the graph, just ignore the other half, and just double this area. That makes sense, right? Because if you look at this is the line that's dividing it, this area here in red, let me put it in red, this area in red here is the same exact area as the one in blue. So instead of going from negative a to a, or in this case negative pi to pi, you can just integrate from 0 to pi, or 0 to a, and just double it, because this area is the same as that area, so the overall area is just doubling it. That's all that this is saying. So again, this may seem like who cares type of property, but it's very powerful and it's going to have a lot of properties. And now arguably the next property is even crazier. It's used even more because it allows you to get rid of a lot of complicated terms. So this is one property. The second one is going to be very similar. So now instead we're going to look at an odd function. Instead of even, we're going to look at odd. Is odd. So that's the key property here, is it's an odd function. And then in this case, instead of being symmetric about y-axis, we're symmetric about the origin. And let me explain what that means. Okay, suppose you have an odd function, it means it's symmetric about the origin. So the definition of odd is this. So this means that a number and its negative are, their outputs are opposite in sign. So the inputs are opposite and so are their outputs. So for example, the cubic function x cubed, if you look at f of 2, that's 8. If you look at f of negative 2, that's negative 8. So see, 2 and negative 2, they're opposite in sign, and so are their outputs. So that's what it means to be an odd function. That's what this jam of symbols means. Okay, and what this means about the way the function works is the following. So this is what x cubed looks like. Okay. So being symmetric about the origin means this. it means that if I flip this function first about the y-axis, meaning I would get something like this. So flip it about the y, you would get this, right? Get this thing, flip it on this side, and then that thing would flip there. And then you flip it about the x-axis, you should get the same thing. So notice if I get this thing and I flip it about the x-axis, this will come onto here and this will go down there. And so I do get the same thing. Or vice versa. So the order of the flipping doesn't matter. So I could instead first flip it about the x-axis. So we flip about the x-axis, you get something like this. So this would come down here. This comes down here, and then this goes up. And then you flip it about the y. So if I flip this about the y, this would go there, and this would go here. And then you also get the same thing. It's symmetric about those two flips. First the flip over the y and then the x, or x then y. So when you flip it in both of the directions, then you get the same function. That's what it means to be symmetric about the origin. So again, if you have the formula for the function, then explicit function here, x cubed, then you can check whether it's even or odd by checking this property. Or if you have the graph, you can check it by checking this geometric property about the flips and things like that. Okay, so either way, suppose we have an odd function. Then this would be true. Smack dab 0. Okay, and again, this makes a lot of sense if you graph what's going on. So another example of an odd function is sine. So let's look at sine x. And let's look at it on the same interval, pi to negative pi. So sine peaks at 1 here, starts off at 0, and then hits 0 again. So it looks like this. And then, you know, because of the properties of it being odd, we know that it basically has to look like this. The negative half of it has to look like this. Okay, or you know, you just use what you know from trig to fill this out. But this is what sine looks like. Now notice on this interval here, negative pi to pi, negative a to a, the amount of negative area is the exact same as the amount of positive area. So what is the net area? 0. Okay, so that's all the theorem is saying, but this is really, really useful. It comes in handy a lot, so it shouldn't be something that like, yeah, I know it seems random, but it's a very useful theorem. Okay. And so the last thing is a bit of notation. Or I guess a definition. So when we look at an interval in the form negative a to a, so these intervals like negative pi to pi, negative 2 to 2, negative 7 to 7, these are called symmetric intervals. So it's just a bit of fancy wordage that I'll probably use, so, and it'll make you sound really smart. Oh, symmetric intervals. So it's good to know. So these are called symmetric intervals, and so we can say that we know properties about even and odd functions. The integral of even and odd functions over a symmetric interval, we have established certain results about these. So let's do some examples of this. So suppose we want to find this integral. Okay, so immediately, anytime you have a symmetric interval, you want to think, okay, maybe I can exploit this property. So let's see whether this function is even or odd. But, functions can be neither. Not every function is odd or even. It can be neither. So don't be fooled and think, oh, it has to be even or it has to be odd. That's it. That's not necessarily true. Okay, so to check whether it's even, let's find what f of negative x is. This means replace every x with a negative x. So if we do that, maybe I should put this in a different color for clarity. So what is f of negative x? So replace this x with a negative x. So it becomes the quantity negative x to the sixth. Right, because this, remember, x just means something. In math, again, it's just a shorthand. It could be as complicated as you want it to be. This just means whatever your input is, you're raising it to the sixth power. In this case, the input is negative x. So that entire thing, negative x, that whole thing is being raised to the sixth power. And then plus 1. So then we know that this just gives x to the sixth plus 1. Okay, well, that is the same thing as f of x, right? The original function. So we have shown that f of negative x equals f of x. So this function is even, is what we know now. So this is an even function. And it's not a coincidence that this power is even and this is an even function. Now, not every function that has an even power will be even. Like if it's an even function, like an even power plus an odd power, that's not going to work. That will be neither odd or even, but it's good to just know that little bit. Okay, so this is an even function, meaning by our theorem or our result that this is really just twice the integral from 0 to 2 of this guy. And then this is twice, and then what's this integral? I don't think we have to break it up anymore at this point. I think we're comfortable just doing it all in one go. So this is 2 times, this integral is 1/7 x to the 7th, and then this just becomes x, right? So if you want, you can distribute the 2. So if you distribute the 2, this is valued from 0 to 2. If you distribute the 2, this becomes now 2/7 x to the 7th plus 2x from 0 to 2. Okay? And then this is 2/7 times 2 to the 7th power plus 2 times 2 minus, so that's one entire quantity. That's one entire quantity minus, now stick 0 into this. Well, you might pretty immediately see what's going to happen. Maybe I don't need to be that careful. If you stick 0 in here, this goes to 0, that goes to 0. So you get minus 0, effectively. And that's what's nice about this is, usually, not always, but if you have 0 as one of your limits of integration, many times just sticking that into the function will kill a lot of it, or all of it maybe. Okay, so then overall you get 2 to the 7th times 2 is 2 to the 8th, and then plus 4, and who knows what this is. I mean, this is just some crazy monstrosity. We'll just leave it like this. Apparently though, if you work through all the details, you get 284 over 7. Okay, so again, This is the calculus part is what I mostly care about. The arithmetic, not as important. Okay, so that's the answer. And then now let's do an example. Another one which you may guess, if we did an even example, we're going to do an odd example. So suppose we want to find this. Okay. Now, none of the techniques that we have developed in this class, nor I don't even know if they're. This is a hard integral. Let's just say that in general. I don't know how if there even are the techniques that we established in this class that allow us to solve this. But either way, you notice that this is a symmetric boundary or a symmetric interval. And so you should try and check whether it's odd or even. And I'll give you a hint, since the last one was even, this is probably odd. So let's see. What do we need to show? We need to show this. That f of negative x is negative f of x. So essentially what this means is if we stick negative x into our function, we should be able to factor out a minus sign in front of everything and have that minus sign multiplying the original function. So let's try that now. So f of negative x is tangent of negative x over 1 plus negative x squared plus negative x to the fourth. Okay, now if you remember your trig, tangent is an odd function. And just from this right here, an odd function, that means the minus sign you can just pop out. See, the minus sign popped out in front of the function. So tangent of negative x, the minus sign just pops out. You get negative tangent of x. And then both of these, since they're even powers, you just get x squared and x to the fourth. Okay, and then what does this allow us to do? We get minus now, a minus sign, pulled out all of this, times the original function. Bingo. We basically shown this, right? Because this right here is the original function, f of x. So we have minus f of x. So f of negative x is negative 1 times f of x. The minus sign just popped out in front, basically. So we know that this function is odd. Okay, and now this is super easy. We just know that since it's odd over a symmetric interval, this is just 0. Nice and easy. That's the answer. So this is pretty nice. You just be like, oh, it's 0 because it's odd. Very nice. Okay, so let me check on the time. Okay, so next up, we are done with chapter 4 now. So we established a lot of things, right? We talked about how to find the area under the curve. That was the biggest problem we wanted to do. And we figured out a systematic way to do that. And it involved the antiderivative, and what culminated in was the fundamental theorem of calculus. So, super important theorem, and it basically made the process of finding the area under the curve very straightforward, as opposed to using those annoying Riemann sums. So now we want to see how you can use the integral calculus to figure out things about geometry, like volumes and areas and things like that. So this is going to be very interesting because you're going to see a lot of seemingly hard to get volumes. Like, how the heck do you get a volume of like a sphere? Like, how do you get that? There are many ways, but calculus makes it pretty quick. It makes it like, something you can do in like 2 minutes, as opposed to the other methods, which I'm sure are much more laborious and hard. So we'll see how the things that we've applied get used a lot in geometry. So to start, we're going to talk about the area between curves. So this is a new chapter. Oh, sorry, wrong color. So the area between curves, okay? And so let's make clear what that is now. So say we have, a function, and then we have, not just one function, we have two functions. So we have one function, f of x, and then another function, g of x. And we're considering them both on the interval a to b. A to b. And say that we want to find the area between these two functions from a to b. Well, I should put it b a little earlier. There we go. Sorry about that. So say we want to find the area between these functions, or these curves, right? Because a function in general is just some curve. So we want this. So the question is, what is the area? What is this green area? How do you find it? Okay, so let's go back to the fundamental way we thought about finding area for a second. This is why we talk about it. If we just never explored how to fundamentally do this process, then a lot of things would be not so great, we'd be left in the dark. So it's good that we developed this from scratch. So let me redraw this. So this was g of x, this was f of x. Okay, and then here was A, here was B. Okay, so if we want to find, this, again, I should have put B a little earlier. Sorry about that. So if we want to find this area here, what are we going to use? Our trusty friend, the Riemann sums. And what were the Riemann sums? They were just the sums of areas of rectangles, right? We just added up the area of a bunch of rectangles. So in general, we want to pick some width, right? Like, we're going to chop this interval up into n pieces again. So we have, right, this guy here. We have a rectangle. Now the question is how high to make our rectangle. So let me just draw a random one. Sorry. Okay, so again, we said that this width here is delta x, right? The width of this guy here, from here to here. So the width is delta x. That's fine. That hasn't changed. Now, The height might, we're going to change this a little bit, but I just drew a rectangle for a second. Now remember, what we did is we chose some point, some sample point, right, within this interval. From anything from here to here, we pick some sample point. Let's say we choose this point x sub I, so let me make it in green, I guess. We chose the sample point x sub I star. And so what we want to do is this corresponds to this height right here. This height here. So we're going to modify this rectangle to have the corresponding height here. Remember, I told you it's probably going to change. So slightly different. Okay. And so this goes down. So x sub I is here. So we go down to this point. Okay. So this is our rectangle. So how high the output is on F and how low you go on G. So what is this point? This point right here is F of x sub I star, right? How high you go is stick this number x sub I star into the function F. That's how high you go. Like that's how high you go. I should put it here instead. Okay. So the height, this piece goes up, you know, whatever this number is, 2, 3, 4. You stick this number, say it's like 1/2 into F and you get a height. And then you do the same thing as you stick now this guy into G, so this is G of x sub I star. So this point here. Okay, so then what is the height of this rectangle? Well, it's this guy minus that, right? Because this is an inherently negative number. So if this is like, for example, 2, and then this is like 3. Sorry, negative 3. So this is 3 and that's 2. So it's 5, right? So you're taking 2 minus negative 3. And what is that? This is f of x sub I star minus g of x sub I star, right? 2 is this guy, and negative 3 is that. So in general, the height, oops, I didn't cover that hopefully. So hopefully you see this now, is that the height here, the height is f of x sub I star minus g of x sub I star. Okay? So we get that. And this would work if this function was like always positive too, right? Say this was like 1. So you just get 2 minus 1. The height would be 1 if you shifted this all the way up to 1. So that the graph looks like this. So it being like negative like this, it doesn't take away from the generality. So we see that in general, a rectangle has width delta x and height f of x sub I star minus g of x sub I star. So the Riemann sum, what is the Riemann sum going to be? The Riemann sum is this. Remember, is delta x times the sum of this guy. because this is the width, which is always the same, and these were the heights. So remember, we take the limit as n goes to infinity to get an infinite amount of rectangles, yada, yada, yada. The moral of the story is, after all of this, is that the area between the curves is going to be, remember, delta x gets replaced with dx, and the heights go here. And the heights in general were some f of x by star, but remember, we just drop the star and just make it f of x minus g of x, this whole quantity. So this is like f of x by star minus g of x by star. These are the heights. You multiply this by the widths. And then this integral sign, remember, meant, add up things, add it up. So the sum, the sigma, got replaced with that. So, and then this goes from A to B. So this is super important. Okay. Now the form of writing this is a little clunky because you might be like, well, what is F? What is G? And so a lot of people like to write this in the following way. They let y sub t stand for y top. So, if you have a function f of x, that gives you some y coordinate. For every input x, you get some y coordinate. For example, if your function is x squared, if I stick 1 into here, for x is 1, you get a y coordinate 1 squared. If x is 2, you get the y coordinate 2 squared, 4. So these guys, the function f of x tells you an output, a y. So, you can write f of x as y. So y top is like the curve, the top curve, which was like f in our example. And let YB, you guessed it, Y bottom, that's going to be like G. So the other function that gives you a Y coordinate is Y bottom. And so a lot of people like to write this way. The area under the curve is this. Y top minus Y bottom dx. Because then you don't really have to be like, okay, what is F, what is G, like what are you talking about? It makes more sense to talk about the top curve and the bottom curve as opposed to just some random letters F and G. But this is just for motivation. Okay. So let's do an example of this. Let's see how this is done. Because there's no way to learn math like just doing examples and practicing. Best way to learn math. I guess that's true for a lot of things too, Okay, so we want to find this. The area of the region bounded above y is x squared plus 1 and bounded below by y equals x. And bounded on the sides by x is 0 and x1. Okay. And these kinds of problems are going to come up continuously throughout calculus. So it's good to get good at them now. Because these kinds of concepts are going to be really useful, especially when you go into higher dimensions where you will do a similar analysis in by looking at certain dimensions and then putting it all together. But I'm going to shut up about that. That's not the content of this course. But if you understand 2 dimensions, you can kind of do this in a higher dimension is what I'm saying. But let's shut up and continue with this. So let's graph this to see what region we're actually trying to get. Okay, so x equals 0 is this vertical line. So this is x equals 0, okay, aka the y-axis. And then x equals 1 is this other vertical line at 1 unit to the right. So x equals 1. So we're trapping the curves between these guys. And now what does x squared plus 1 look like? Well, let's just plug some numbers in. If you stick 0 into here, you're at 1. So it's 1 unit up at 0. And then if you stick 1 into it, you get 2. So here's 2. So then it goes to 2 here. Okay, so it looks kind of like this. It's a little curved. And then what does y equals x look like? Well, that's the simplest line, right? This is a line with slope 1 and y-intercept 0. But again, let's just plug numbers in. So if you stick 0 into here, you get 0. And if you stick 1 into here, you get 1. So the line looks like this. Not as linear as I'd hoped. There we go. Okay. So we want the region bounded between all of these. So this is x equals 0, this is x equals 1, and in between these two guys. So putting this all together, we're interested in this region here. We want this area in blue. Okay? Now, what we should identify what the y top and the y bottom are. So y top is x squared plus 1, and y bottom is just x. So we're in business now. We can definitely calculate this area using the formula that we have. Now, before I erase this stuff, let's just set up what the integral should be, and then we'll work it out. So the area is going to be, we'll think about the limits of integration in a second. It's going to be y top, x squared plus 1, minus y bottom, just x. All right, y top minus y bottom. Now, from what number on the x-axis to what number on the x-axis does this begin and start? Well, it starts at x equals 0 and goes all the way until x is 1. So this is going to be the integral from 0 to 1. This is the area under the curve. Is given by this expression. This blue area is given by this expression. This is the beauty of calculus. This is amazing. How would you ever find such an area without this method? It's crazy. Okay, so let's just work this out. Calculus has reduced this incredibly hard geometrical problem into a little bit of algebra and a little bit of arithmetic, basically. It's incredible. Okay, so then we'll just do this. Restart from scratch. So we have the integral from 0 to 1. Okay. So then again, we could break this up into 3 different integrals, but I think at this point we've gotten the hang of it. We can see that we can just do this all in one go. So this is 1/3 x cubed. This becomes x. And this becomes minus 1/2 x squared from 0 to 1. Okay? Now this is just plug 1 into all of this. So this is 1/3 plus 1 minus 1/2 minus, what happens when you plug 0 into all of this? Well, you just get 0. Okay? So then this, the common denominator between 1/3 and 1/2 is 6, right? So this is like 2/6, and then 1 is the same as 6/6, and then minus 3/6. So overall this gives, what? 2 plus 6 is 8, minus 3 is 5, so 5/6. So the area of this thing is 5/6 units, or whatever units we're using here, like feet or whatever. So that's incredible that we can get that, the area of that weird oblong shape. But that's the beauty of calculus. Okay. Now let's do another example where now finding the limits of integration won't be as straightforward, but it's not the end of the world. Check on time. Okay, so I think we'll have time for this example, and that's it. So we want to find the area find the area of the region enclosed by y equals x squared, and y is this. 2x minus x squared. Okay, so notice here they don't give us like x equals 0 and x equals 1. So we need to kind of draw this out and see what this region is, what this enclosed region is. Okay, the key to doing these problems is step 1 is to find where these curves intersect. Because if you can find that, those will be the points that close off your region. So step 1 is to find the points where the curves intersect. Or maybe I shouldn't number it because I might forget, but we need to find curve intersection points. Okay, so where do these guys intersect? And so what's the best way to find when two functions are equal to each other? Well, just set them equal to each other. So we're going to take x squared and set it equal to this. Okay, now if we do some algebra, this is the same thing as 2x squared minus 2x equals 0. Right, add the x squared and then subtract the 2x. Now we can pull out x in this. Oh, actually you can pull out a 2x. So just be left with this. Okay, so what does this tell us? This means that x equals 0 and x equals 1 are intersection points. Okay, so we know that these curves intersect at 0 and 1. So this will kind of bound. This is where the boundary will be at. Okay, so we know that if we stick 0 and 1 into these functions, we should get the same output. So if you stick 0 into here, you get 0. You stick 0 into here, you get 0. So at the origin, both functions assume value 0. And then same thing for 1. If you stick 1 into here, you get 1. If you stick 1 into here, you get 2 minus 1, which is also 1. Okay, so we get this. Okay, so the two curves have the same value at these points. That's what we found. Now, let's think about maybe an intermediate point, because we need to figure out which curve is on top and which curve is on bottom. Okay? So, if we look at an intermediate point, let's say 1/2. Let's pick 1/2 for example. So, if you stick 1/2 into here, you'll get 1/4, right? So at one curve, the value is 1/4. On the other curve is what happens when you stick 1/2 into here. You get 2 times 1/2 minus 1/2 squared. So you get 1 minus 1/4, which is 3/4. Okay. So in the other function, we're actually all the way up at 3/4. And so this might be enough to kind of show which function is the top one and which one is the bottom one. It's, it's a little subtle because just because one function is on top of the other for a little bit doesn't mean it always stays on top. It could dip down below. And we'll see examples of that. But we know that both of these functions are parabolas, right? They're quadratic functions, so they represent parabolas. So just using this piece of information, we can kind of stitch together that this is really what's going on. So maybe we'll make this one red. So this one is red. And so we have this one. So this is y equals x squared. Now let's make this one blue. So this one's blue, and then, so we know that it has a value of 3/4 here. And also, because you can rewrite this as negative x squared plus 2x, right? So this is a parabola that opens downward as opposed to upward. See? This parabola opens up, this parabola opens downward. And because we know it opens downward and it's larger than the other one, it has to look something like this. This arc was a lot better than my other arc. See if I can fix this one. Okay, sweet, there we go, dead on. So this is the enclosed region that we have. So the area that we're interested in is exactly this one. You can see the rest of the curve, like, if we continue this guy is going to come up here, right? The parabola looks like this, it's symmetrical, right? It comes up here, and then if you stick, like, say -1 into this function, you get 2 times -1 minus -1 squared. So that's -2 minus 1. That's -3. So the blue function goes down here. So notice that this region is not being bounded. And then same thing, if we continue the red curve, this is going to go up like this. And then this guy goes like that. So no region is being bounded anymore. Where the region is being bounded is exactly between 0 and 1. And that's why finding the intersection points is so important. It shows us basically where we need to focus our attention to on the curve. Because the rest of the curve, there is no region being bounded. These things get separated from each other very largely. So we want this area. That's what we want. Meaning that the area that we're interested in, again, has a straightforward expression because we have a y top and we have a y bottom. So we know that the area is from 0 to 1. Again, x is 0 to x is 1. Y top was 2x minus x squared minus y bottom, which was just x squared. So this was y top. This is y bottom. Okay? And so this is just 2x minus 2x squared. Okay? And then I'll leave this as an exercise to you guys, but when you do all of it and everything, you end up getting 1/3. So this area in the green is 1/3. Okay, so that's pretty neat. So sometimes you'll have to determine the limits of integration and this region by graphing, as opposed to just being given like all of the pieces. So it's good to have seen that example. So next time we'll look at some more trickier examples and what happens in the case where, you know, if the curves kind of are sideways. So like, for example, if you're interested, if this is one function and let's say this is another function, and you're interested in this the area of this region here, sometimes it may not be as straightforward. So we'll see kind of like what happens. Maybe a better graphic to demonstrate this is just being generic is, say you want like the area, like this kind of area. So you have like curves that go like this. Maybe I'll make this red. One curve like this and another curve like that. And you're looking for the area like this area here. So maybe kind of like a cylinder or something like that. Like a, kind of looks like cylindrical. So we'll see how to deal with this, because here it's hard to see what a y top and a y bottom is. So we'll talk about that and some more examples next time. Thank you.